Okay. So the main thing that we had been looking at in probably last couple of classes is what we called as rectilinear motion. And we said that it's essentially a motion on a straight line, a straight path. So this is essentially the direction of your arc length or the velocity or the acceleration, all of which those were in not the arc length, but the position vector, for example, which leads to the arc length from some origin in a inertial frame of reference. So all of what we will be doing in the remaining part of the course is very similar to most engineering subjects. It's essentially generalization of the physics and maths that you have learnt in high school. It's just making it a little more applicable, more complex, and also the methodologies you're trying to refine and get to more realistic cases, especially for aerospace engineering kind of applications, right? So for example, eventually you'll be looking at an aircraft which is going to be pitching, which is going to be yawing, and which is going to be rolling. And if you see the correspondence with the concept that we introduced in the previous class, which was essentially a 3D space curve in which, let's say, any particle is moving. What we are doing right now is that particle, we will try to extend the concept to eventually rigid bodies, and eventually in other courses you'll expand it to elastic bodies. So when you're trying to concentrate a rigid body into a particle or a point, essentially what you're doing is you're talking of a center of mass that goes with it, right? And the intrinsic or natural coordinates that we introduced with this were what I called as T, N, and B, and we introduced the Ferré-Serre formulae, which gives the derivatives of these unit vectors in terms of themselves, in terms of how simple it is by just introducing two parameters to it, which is what we called as the curvature and the torsion. Now, from an aircraft point of view, considering or idealizing it to be a rigid body first, and secondly that rigid body to be concentrated at its center of mass, you know that there are three rotational motions and three translational motions for any rigid body or any particle which is idealized to be that rigid body. Even though it's a particle by itself cannot have rotations, because it's a rigid body that we are focusing at the center of mass and considering it to be a particle, therefore we also have 3 degrees of freedom associated with the rotations. Now, if you look at the concepts that I introduced over here in terms of the curvature and the torsion, they have a very direct 1:1 correspondence with an aircraft motion, and you will see that very clearly when you go to courses which are going to be built upon the dynamics. And that is, for example, you have this pitching motion. This pitching motion is essentially something which helps you to change the angle of attack and therefore the speeds of the aircraft. And I think one of you, I think Sid, probably presented that pull-up maneuver in the previous class. So you presented this pull-up maneuver, right? So it's essentially a circular path motion. So when you're trying to do that, when you're trying to change any velocity or the altitude, essentially you do that by changing your pitch, which is deflecting your elevator, right? So now that is only going to change your velocity and through an acceleration, which either can be a constant or anything which is non-zero. It could be a function as well of s and or time. But the pitch is not going to be helping you directly with the maneuver. What is actually helping you is also the roll and the yaw, and that is what can take you onto a 3D curve, unlike the pull-up maneuver, which was entirely in the longitudinal plane, which is the plane of symmetry of the aircraft, and therefore there is not too much of a complication from the rotational point of view. The rotation was entirely to change the speeds and the altitude to get into a circular path from what was a rectilinear path. Okay. Now these two paths, whether it is circular or rectilinear, actually is once again a generalization. So the reason why we are introducing this kind of a coordinate system, polar, and later on for 3D bodies, the cylindrical coordinate system, and also the intrinsic coordinate system that we talked about, either in a 2D planar motion we need only t and n, or in a 3D motion we need t, n and b, can be thought of as generalization of the rectilinear motion, or in other words, if you go step by step from rectilinear motion to circular motion. So let's say this is going on to, instead of the straight line, it's going on to a circular path like this. So it's entering into this. It may not complete the entire circle, but essentially a circular arc that is completed. So let's say this is the center of the circle of a particular radius, which we will call as, let's say, rho. Now if you look at it, you can always think of the rectilinear motion as a special case of that circular motion. What would be the requirement for that? What would be the limit that a circle becomes a straight line? Yeah. So it's quite obvious that in the limit as rho tends to infinity, your circular motion becomes your rectilinear motion. Okay, and this circular motion that we are talking about is planar, within a plane. We have not yet gone out of the plane of this whiteboard or into it, which means that this curvature that we introduced in the previous class, which we said was when you take the derivative with respect to the arc length s, which we denoted by prime, as opposed to dots, which were derivatives with respect to time. So then you ended up with antisymmetric matrix. We will come to the other ones later. So the first generalization that we are doing is to introduce this curvature. So equivalent to saying rho tends to infinity, what is in terms of kappa? Rho is the radius of curvature. While this is the curvature.
Zero.
Right?
It goes to zero.
Yeah. Did I use the microphone? Yeah, is it? Okay, fine. Thank you. Yeah, so that tends to zero, right? So these are two equivalent ways of saying the same thing. What does it mean as far as this matrix is concerned? So if it's a planar motion, then you don't have the other term as well. We will come to that later. So it's a planar motion. The only thing that you have is the curvature. Now, if you're moving from a circular motion to a rectilinear motion, all that you're doing is you're setting this as well equal to 0. So what does it mean? The entire matrix now becomes 0. So what does it mean? Sorry, this is going to be multiplying t, n and b, all of which are unit vectors. Okay. So what does it mean? And what is this mathematical equation? What does it physically mean? So you have a null matrix, all zeros, multiplying a vector. What will the right hand side be? Be a vector of zeros, right? A column matrix of zeros. So what does it mean? So all of these primes are 0. So what does it mean?
There's no change.
Absolutely. So your T, N and B are unchanged. What does it mean? So you are entering a rectilinear motion where the tangent remains the same with respect to this. So if you are using this as the coordinate system, this J hat is the direction in which I have drawn your S, V and A. So you are ending up with rectilinear motion. So always remember that throughout the course, whatever concepts we introduce, from the basics, physics and maths point of view, it's all there. You already did it in your high school. It's only just, you're just making things little more generalized in nature. So when you're moving from rectilinear to circular, it's not that you're going to an entirely new topic. You're just generalizing that. And if you want to put the appropriate things in the limit, then you would see that you are going to be reducing your circular motion back to what you already know about rectilinear motion. So when you start thinking from that perspective, things become much more tractable, and the pedagogic tricks of learning becomes so much more easier for you to grasp. So that's very important that you remember that. Now, the next level that we will go from 2D, for which we will need polar coordinates, of which we talked about briefly already, but we will go in a little more formal sense and some more equations associated with that. The next step that we will do is to go from 2D to 3D, and a normal and a direct extrapolation of that is essentially using the cylindrical coordinate system instead of the polar. So it remains the same in the XY plane with your r and theta, just that just like the Cartesian coordinate system as an x3, or what is also in most cases called as x, y and z. So you're on the z direction, you're essentially going away from the x1, x2 or xy plane to the x3 or the z plane, and introducing one more unit vector k coming up with it. And in general, that motion can have some kind of a change in the z direction, and that's where we introduce the other quantity, which is tau. And let me just erase this. There's another convention that some books and or some literature might use, that they may interchange the signs of these two. So the way tau is defined as plus or minus can be different, in which case this would become minus tau and this would become plus tau. So don't get confused. It's just interchangeable way. It's more of a sign convention. So whichever is comfortable or convenient to you, you can stick to that, but just you have to be consistent with that throughout a particular derivation. You can't change it in between. So that's the whole idea. So now what is happening when you're first introducing kappa, a non-zero kappa, that is, you are moving from rectilinear to circular. Now when you introduce a tau, you're moving from a 2D motion to a 3D motion. So that's essentially what's happening. And you could still do with your Cartesian coordinate frame. It is not that nothing, these more complex cases cannot be dealt with it, just that the derivations will become much more messy, and you will lose the advantage of a particular thing being a circular motion or even a circular arc unless and until you either go to a polar system or at least a TN system. In many cases the TN system might be even more simpler and easier to handle. Once I give you the equations, you will see that advantage over the polar. So there is an advantage going from Cartesian to polar in 2D or cylindrical in 3D, and there's also an advantage in going to the so-called intrinsic or natural, which is essentially this TNB system that we have talked about over there. And you introduce these quite normally, very simple, because you already know what is a position vector from some origin O in an inertial frame. O is fixed, and from that fixed point of an inertial frame of reference, you're going to the current location of the particle or the center of mass of a rigid body. So now that center of mass, as we were talking about in the case of an aircraft, what the pitch was essentially taking care of just changing your speeds and altitude, but now the roll and the yaw that you're going to have is what corresponds to this. So your yaw is essentially similar to your curvature and your roll is essentially similar to your torsion. So, and again, you'll be doing structures related courses later, like 3140 structural analysis, where you will be looking at from a beam point of view. If it's a structural beam like what you have running over the room over here, taking the load of the floor that is above this. So you are seeing that that is essentially undergoing bending. It's essentially a long slender structure like this, where one dimension is much larger compared to the other two dimensions. In a dynamics problem, you'll have to compare actually wavelengths rather than actual lengths, but let's leave that complication aside for now. But right now, you are essentially saying that instead of a 3D body, you can deal with it as a 1D body. And this can be initially curved and twisted. So that initial curvature and initial twist will come into this. So all of these things are related. So that's what is very, very important for you to see. It's not only through that pathway that we were talking about, going from say differential calculus and physics and or statics to dynamics. So that's almost entire body of knowledge goes there. But even going from dynamics to so-called almost looking like unrelated topics like structural analysis, there are a lot of mathematical modeling techniques which are alike, and if you have mastered it in one course, then it's very easy for you to get to the most complicated things in structural analysis, for example, very easily if you're able to do this. And all kinds of 1D structures, not only beams like this, but torsion tubes or shafts, or even columns like what you have compressive load on those. So all these kinds of complications can be dealt with. Even axial rods which are under tension, for example, like the helicopter rotor blade, etc. Many of those can be handled with these systems. So the simplest system that you can have is in an inertial frame of reference, a Cartesian coordinate system, but the complications in going to these are actually going to be quite advantageous. And there is another pathway that you can take. Instead of going from polar to cylindrical, you can instead go from polar to spherical. So wherein here the additional term that you had was the z and k hat, here you are going to have another angle that is going to be associated with it, and a unit vector that is going to be associated with the same. So we call those two angles now. What you already had in the polar is called the azimuth angle. So that's your theta. So this is called the azimuth. And now you are going to have an additional angle that is going to come over here, which is typically the polar angle. So because it's associated with a pole that you introduce, and this is something that is going to be of great importance when you're looking at space dynamics. As part of aerospace, space dynamics is very critical, and most of the spatial motion of, let's say, satellites around a planet or even a planet around the star like sun, all of these are essentially motions which are involving spherical bodies and therefore certain spherical symmetries, and many a times it might be very convenient for you to go to a spherical kind of a coordinate system. So keep this in mind, how it is kind of branching out. You're trying to go from a 1D problem, rectilinear, to a 2D problem, which is circular, simplest case, but it can be non-circular problems as well, in which case more than the polar, your intrinsic or the natural coordinate system will be much more relevant in that particular problem. So this is as far as the overview of what we are going to do probably in today's and the next class are concerned. Is there any doubt on this? Yeah. So the other thing, other generalization that we are going to do is, we have been dealing only with kinematics so far, which is a description of the motion. Now we are going to also, probably in the next week or the week after that, get into kinetics, where we are going to involve the causation of that motion in terms of the forces and or moments that are going to change the motion, either in terms of the speeds and or the directions of motion, which is essentially causing non-zero accelerations. Now, to understand that, again, it's very simple. So suppose you have a point, or for that matter any body, which is moving in a particular direction. So still sticking to rectilinear motion. So this is, let's say, the velocity of that, and let's say this is a constant. Okay, what does that mean in terms of the causation? If the velocity is constant, can you say something about excellent. So essentially it's your Newton's second law, or what we will extrapolate to Euler's second law as far as rotational motion is concerned. This is neither rotating nor is it accelerating, so therefore it's going to continue at the same speed, right? So it's essentially your Newton's first law also. A body or a particle which is moving at a certain speed remains at the same speed for constant motion unless and until acted upon by an external force. Now let's introduce that force. So suppose you have a force F, either this to the center of mass, you are having a force, so that there is no rotation which is kindled, it's only a translation that is kindled. So what will happen now? What will happen to your V? The way I have shown the force, increase, right? So very good. So you're going to have V increasing, because now your acceleration, which was earlier 0, is now non-zero, and in fact the direction of the force that I have shown, it's very clear that it's going to be greater than 0. That's the value of your acceleration. It may or may not be a constant. It could be a function of time, the arc length, and or explicitly the time and the velocity as well, right? So now that's as far as this direction of F is concerned. Now it's the same thing in the second case as well. Whatever I'm saying over here is valid in the case of the body which is just translating, let's say on rollers, for example, over here. Yeah, so that.
Would the external force cause shear?
Yeah, good question, but that has to wait till structural analysis, because here we are considering all of them to be rigid bodies, right? So when you're dealing with them as rigid bodies, the force is only going to cause an acceleration and therefore a change in velocity, okay? But it's very true that in reality what will happen is the body is not actually rigid body. No body is rigid, in fact. Some are more flexible than the others, that's all that you can say. But so essentially in such a situation what will happen is, as long as this is friction free, a frictionless path, it might still move without any deflection. But once there is friction, there is going to be a certain resistance, and there's going to be a moment about it, and all kinds of stresses will come in, and shear will be one of them. Yeah. So yes and no is the answer to your question, right? So it depends on the idealization that you have. In reality, yes. Yeah. So now we are not getting into those complications. All that we are doing now is one step at a time. So your force is in the direction same as the velocity. It's a rectilinear motion, and once again what happening is, based on Newton's second law, your acceleration is non-zero and your velocity increases, right? Now what happens if I have a force like this in the same, passing through that, of course, and let me not complicate it, right? Yeah, so you're going to have a decrease in velocity, and A is once again non-zero, but this time it is a negative value, right? It's deceleration or retardation as we call it. So that's essentially what's happening. Now this might look too oversimplified to why am I stressing on this, but there is a reason, because that's what is going to lead us to this. What is the commonality between the forces that I have shown in these two? These two cases, what is the commonality?
Same magnitude?
It may or may not be of the same magnitude because I'm using the same symbol. That's right. That's one of the things. But in terms of direction,
Is there
yeah, exactly, right. So it's collinear to the motion. So the motion is already rectilinear, and what I'm trying to change it with is collinear with that. Okay. So when I have something which is collinear or essentially parallel passing through the path of the motion, that's going to only change when I say v is increasing or decreasing. It's a vector, remember. So what am I actually saying? I'm actually talking about the magnitude of v over here, right? The speed is what is going to increase or decrease, right? But vectorially it's going to remain in the same direction, right? Now I'm going to no longer keep this rectilinear. In other words, the force is no longer collinear. I am going to change the direction of the force. These are two extremes I had, in the direction of motion, opposing the direction of motion, but I can have it anywhere in between, right? So some arbitrary direction, and the extreme case of that is when this force is perpendicular to the path of the motion. So what happens when I have it along the path? It increases the magnitude of the velocity. Opposite to it, it decreases the speed. Now what is going to happen when I have it perpendicular to the path?
Change direction but not speed.
Excellent. Yeah. So it is going to change your direction, and essentially if no other force is acting, and that's the only force which is acting on the particle, or for that matter on the aircraft, let's say, then that's what you have from an aircraft which is taxiing or even getting to the takeoff speed on the runway, and suddenly you have your lift which is perpendicular to that path on the ground, and essentially it's moving up. Because remember, lift is always defined as the force perpendicular to the velocity direction, and your velocity on the ground, as the landing gears are, the landing wheels are on the ground, it's essentially horizontal, and then you have a vertical force which is perpendicular to that, and essentially the takeoff. And except VTOL or STOL aircraft, tall aircraft, or for that matter, you're typically going to have a curved path that is going to be there, right? So in the case of rocket engines, there was no initial motion. The speed was zero. The Falcon example that you worked out in the homework, essentially it's going up, and then at a particular point changing the direction to 45 degrees, right? Now here what we are talking about is there is already a non-zero speed at which it is traveling on a straight line, and now you are applying a vertical force, and that's going to essentially change it from rectilinear to a circular path. Okay, and that could be not an entire circle, it is essentially a circular arc. Yes, Siddharth.
And if it were moving at the same speed in a circle, like uniform circular motion, the magnitude would be zero, right?
The magnitude will be
For the
zero.
acceleration.
Yeah. So magnitude, see, acceleration is again just like velocity, it's a vector, right? So a vector involves two parts to it, the magnitude and the direction, right? So you have to see exactly how that force is going to vary. So if that force is only perpendicular, we will see the expressions for the acceleration, which will have both components which are along as well as perpendicular, but the one along is going to be zero. So that's where you come up from, which means that your speed is going to be a constant, right? So your speed is constant, but the velocity itself is changing direction, and because velocity is changing direction, the velocity vector is changing, which means there will be an acceleration. And that acceleration is what we will introduce today, a very important concept called centripetal acceleration. Okay?
So what's the angle, because the angle is changing, the velocity is changing, so that it is acceleration.
Exactly. So like all vectors, velocity has magnitude and direction. So a change in velocity either through magnitude or direction or both can mean that there is an acceleration, right? And that acceleration in turn means non-zero acceleration in turn means that there is a force which is exerted, right? An external force which is acting on the system. In this case, our system is just a single particle. We'll soon move to system of particles, and a special case of that system of particles is a rigid body, because a rigid body consists of many material points. Each of them can be thought of as a particle, and all those particles put together form the rigid body, just that there is a constraint because it's rigid, that the distance between any two arbitrary points will remain the same. So therefore, there is a certain constraint under which this particular rigid body will move as opposed to an elastic body. So that's what is the situation. Whenever there is a force, there is going to be an acceleration. That acceleration could mean either the speed changes or the direction of the velocity changes, or both. Okay, so in this special cases that we have looked at, where f is collinear with the path, only the speed changes. Where it is perpendicular, only the direction changes, and that direction change is caused by an acceleration which is called as the centripetal acceleration. Okay, so that's a concept we will soon get into. Okay, have you heard of any other acceleration or force which also starts with this prefix centri? Yeah. Okay, now what's the difference between them?
Centrifugal acceleration is pushing it away. Yeah, it's outward versus in. Yeah.
Okay. So in fact this word means seeking the center and therefore moving towards the center, right? Whereas this is essentially moving outward, right, as you correctly pointed out. Now, very soon we will see from a mathematical definition point of view as well as from a physical point of view, there is more than that. This is of course talking about the direction, whether you're talking of centripetal acceleration or centrifugal, both 1 and 2 are associated with acceleration or force, right? Equivalently, because they are related by Newton's second law, the proportionality constant between them being the mass of the particle when talking about just a particle. So this is essentially you're only talking about the direction. One case it's moving inward because it is, you see, it's always towards the concave direction. So your force is in this direction, therefore your acceleration is also in this particular direction. And you rightly pointed out, in this simple case where you have a rectilinear constant velocity and then there is a force, this A is going to not change the speed, it is only going to change your direction, and therefore it is non-zero, right? Now that is towards the center of that circular arc, and therefore this is an example of your centripetal acceleration, and this is an example of your centripetal force, right? Now, can you think of a situation where you have a centrifugal force or a centrifugal acceleration? Even before we get to that, what could cause this? We talked about the simple case of your aircraft, which is traveling at a constant speed. Suddenly there is a lift and therefore it is getting into a curved path, right? So your lift is an example of a centripetal force at this stage, okay? Of course in cruise it's a different thing. At this stage, when it's a transition from the at the lift-off point, essentially it is having this kind of a motion, right? So at that point its lift is essentially a centripetal force and it is causing a centripetal acceleration. Turn means that the speed is at that instant remains the same, just that you have reached the top speed and remains the same for that small instant of time immediately after that, and it changes the direction. So it is taking off, it's lifting off, your wheels are no longer touching the runway, right? Now that is an example where you have lift causing, so this F, you are talking of examples for this F, that is centripetal forces. So this centripetal force, one example is lift. Can you think of another example, not in an aircraft, any other body which is moving straight and suddenly there's a force which is perpendicular to that, and therefore instead of continuing straight, it takes a curved path without changing its speed. Very, very good. So lift on an aircraft and gravity on any body for that matter. Yeah. So let's take for example a planet moving around a sun or a satellite, whatever, right? So in those cases, you know it's typically an elliptical path, of which a special case is a circular path, and essentially gravity is the one which is causing that centripetal force and therefore centripetal acceleration, and therefore the velocity's direction to change without changing its magnitude. Another example, a third example of centripetal forces. We've been talking of air and space, aerospace, right? So let's come down to the ground. Any examples from the ground? It's not just aircraft and satellites which go on a curved path, right? Ground vehicles go on curved paths as well. Excellent. So friction is another example where you have, let's say, a curved road on which you have land-based vehicle, could be a bus, car, two-wheeler, whatever. Essentially, you're going on a curved path. If you have to do that, if there was no friction between the tires, what will happen is, or you can think of, let's say on the dashboard, you have placed a cup of coffee or something like that, okay, and it's a fairly smooth surface, hardly any friction between the coffee cup at the bottom and the dashboard. What will happen to the coffee cup or mug? Come again? Spill, yeah. But what direction will the mug move in before it spills? That's the end effect, yeah.
Opposite direction to motion, so to right.
In this way? Yeah. So the mug moves that way, right? And you probably guys on an adventurous ride where there's probably no radar tracking or whatever, you might have tried to exceed the speed limits. And when you try to do that, even if you don't have a coffee mug, you would have observed some forces acting on your body. Yeah? So which direction would those forces be? Same, radially outward. So you are over here. Once again, the force is over there. But why didn't you spill? Friction, right? So your friction, what was your friction doing over there? Your friction was acting in which direction? Frictional force. Exactly. So it's acting towards the center of this circular path, right? So what kind is it when you're talking of these two variations? Centripetal, right? So that's why we said friction is another example of a centripetal force, which first of all, one, it keeps your car from skidding away, right? So there's a friction between the tires and the road, right? So that is causing it to remain on the path, right? And typically these will not be horizontal paths. Have you seen how circular paths, especially when the radius of curvature is very small, or in other words the curvature is very large, what do you do to the road? It's not horizontal anymore, right? You have seen probably in Olympics or something, or even sports where you have cycling, for example, how the cycling paths are. It's more like a bowl, right? So essentially you have a curve. What do you call that? Very good, yeah. So you typically will have banking, right? So that is, this portion will be at a higher altitude compared to the corresponding other end of the road, or lower altitude, right? So you have that slope. So what's that doing? So in that case, where is the centripetal force coming from?
Would be the normal force from the side of the thing.
Very good, yeah. So the normal force will always be perpendicular to the surface on which it is moving, and that will have a component which is going to be radially acting as well. So right, so because it's sloped like this, your force is like this, and which means that it will have a component which is along the towards the center, which is radially inwards, and that's offering you certain centripetal force. So in other words, they're sharing the load. Friction is still there. It's that partly done by friction, partly by banking. And if the banking is very large, the frictional forces might be very small. So the load on your tires may not be that large, right? So the sideway loads, right? You still have the load coming for the forward motion, whatever is there, but you're talking of the sideway motion. Yeah, so
Quick question about the force that we feel outward from the vehicle. That's the centrifugal, or?
we'll come to that. Yeah, yeah. Is it? So you're talking of the mug or the driver over there?
The driver. All going around.
Okay. So is it?
Is it
Think
more-
think aloud about it.
would it- Since it's coming.
It's true that this is inward, this is outward, right? So that's how we are classifying. Both are radial. Okay. That's and so we clearly see that it is outward, right? So the motion is outward over here. So what about the acceleration of the force? Because that's what we are classifying as these two, right? So you're not talking of just the speed or the motion, but is there some force or acceleration associated with that? Those are intricately related with each other. If one exists, the other does, by Newton's second law.
Oh, okay, so it's an equal force, not opposite direction.
Yeah, yeah. So the car is not moving. Yeah,
No, I have just a question, tricky question. So if a particle is going in a certain way, so there is centripetal force
Yeah,
and there is centrifugal also. Like
right,
both are equal.
yeah.
So the forces should cancel and there should be no force acting on the
But it's still going in a circle.
Why is the particle going inside?
Okay, so the same thing. Centrifugal and centrifugal are the same thing. It's just different directions. There's only one force. But no. There's the equal and opposite. So why is it still going in one direction?
Well, you can still have a velocity even if your net force is zero. If you're not accelerating.
No, but the velocity is changing because direction. Direction is changing, so velocity.
What do you mean it's going opposite? If you're going like this, how is there a force that way?
You just said there is a force moving up.
Oh, that's because of the inertia of the object previously. It's not directly attached to the car. It's not a rigid body, so it's going to move. Like it's going to follow the same path it was initially on before the force was applied. So that's why it seems to be moving outward.
Still the mark is also kind of going in the circle, right? It has to do with the frame of reference.
Oh yeah. If you're taking the outside frame of reference, then you're looking at the car. But if you're looking at the inside, the car is not moving. You can't have both of the forces in the same frame of reference.
absolutely. Yeah.
You can't have both of the forces in the same frame of reference. If you're inside the car, sitting inside the car's not moving, right? The car won't
Yeah.
physically move. You're moving.
Yes.
So it's the same force. It's just different frame of reference.
Oh, okay, so you either have one or the other.
Yes.
Yeah. Okay. So now we have looked at 3 examples, right? Lift, gravity, friction. Anything else that you can think of? Air resistance, yeah. In kind of, we talked about it in a different context, yeah. So it's a particular maneuver that you're doing. You could have your drag component also sometimes acting to enable maybe a centripetal. You can define a particular maneuver to do that, yeah. Anything else?
Would electric count? Electric.
Yeah. So essentially you're talking of,
Oh, you mean like how proton goes, like the electromagnetic, like an electron orbiting a proton?
absolutely, yeah. So this kind of spreads over beyond mechanics to other aspects of physics as well, like electromagnetics and things like that, right? So in fact it gets a little more complex over there. When you have a magnetic field and a motion, you could generate electric field or vice versa. So these three kind of get to couple with each other. So let's not complicate things too much over there. So that's essentially what is happening. But if you look at, in one case it was able to maintain because there was sufficient friction, that is between the car and the road. In the other case it was not able, between the mug and the dashboard there was not sufficient friction, and therefore it was moving outward. So in essence, if you look at it, this centrifugal is, which is what is making it move outward, is essentially it's just an absence of centripetal. So the way to remember is it starts with the suffix here starts with an F, which is fugal, and the same letter F can be used to say it's fake or fictitious. You see, it's just talking about, it's like between, if I switch off the lights at night in this room, we're going to have darkness. Does darkness and light either have a different meaning? Darkness is just the absence of light. So similarly, your centrifugal, wherever there is no lift, where there is no gravity or no friction or any such mechanism by which you are pulled inwards towards the center of that circular path, that is what is causing the centripetal force, and therefore a centripetal acceleration, making it move on a circular path. But when you don't have that, or it is too small, let's say the banking is too small, the tires are worn out for this vehicle, then what is going to happen? It's going to skid, right? So that's essentially going to look to us from, as Aditya pointed out, from an inertial frame of reference, which is, let's say, fixed to the road or the earth. From that point of view, it's going to see, yes, it's moving away from the center, so it's more like a centrifugal acceleration or a centrifugal force acting on it, which is why it is moving like that. But in reality, there is just an absence of a mechanism to rein it in. The other example is, I don't have a cable here, but if I were to tie something at the end of a cable and try to rotate like this, what would happen? Initially it's just vertical if I'm not moving, but once I start moving at a reasonable amount of speed, this cable is going to become horizontal, and the bob which is attached to the end of it, a ball let's say, is going to move in a circular path. So do these three cover that? Is there a fourth example over there? Tension, right. So tension in a cable or a wire or whatever you want to call it, a cord. So that's also going to cause it. So what happens, for example, if I'm moving around like that, I also have in my left hand a pair of scissors, and as I move, I cut it off. What will happen to the ball?
It'll shoot forward in the same trajectory that it was cut off.
Yeah, so I have this ball kind of rotating at a certain angular speed, let's say omega, right, about the center, and suddenly I cut it off. Okay, so earlier there was a tension. Now once I cut it off, that tension goes to zero.
The tension is going to cause the centripetal, so if you don't have the tension, it's not going to.
Right, so which direction will it move? Will it, the ball will not, of course, not move on this path, but which direction will the ball move?
Tangential to where it's cut off.
Yeah, yeah. So essentially you are removing a force means you are removing the acceleration. So if it's removed, then the velocity remains the same, which means the velocity's magnitude, the speed remains the same. Of course, you're considering no other forces are there like the air drag and the gravity and all that, ideal kind of a situation, then or that those are negligible or small compared to the tension that we had. Now that is removed, so you're going to have it tangential to the path, but so no longer going to be circular, it's going to be straight line, a rectilinear path, so it's going away from the circle. So again, the absence of the torque look like it is moving farther away from the center and therefore look like a centrifugal force, and once again a fake or fictitious force. Okay, so it's important to remember that fugal, fake, fictitious. Okay, might be strong words, but it's important for you to understand that. Just like we say, doesn't mean we say darkness is fake or fictitious, just that it's the absence of light. It's a perspective. From which perspective are you looking at? Okay, so if you're focusing on light, then you say this is fake or fictitious, but you could have an entire model based on darkness, or you could have an entire model based on centrifugal. Exactly, right? So it's from that point of view. So this is purely from a physical explanation that you see what we are talking about over here, but now we will get into the mathematics as well, and we will see where this appears and how it is very, very clear and crisp from the mathematical model that whatever we are talking about holds. Yeah, any questions on this? Okay, so let's get going. Particle motion in polar, which is 2D, and the extension of that, which is your 3D, which is a cylindrical coordinate system, right? So now when you're talking about polar, let's always start from what we already know, the Cartesian coordinate system. So we want to move to the first polar and then cylindrical. That's first 2D and then 3D. While we are at it, what's the principle of a centrifuge? Anybody? You heard of a centrifuge or probably even used it, right?
You spin it and then you separate different
Yeah.
separate different materials based on their qualities, and then
Primarily density.
densities,
Yeah.
The furthest dense ones go outside,
Mhm.
and that way you can get different substances. Located at different places once the centrifuge is done.
Yep. So essentially what is happening over there in terms of centripetal or centrifugal? So what you explained is correct, but can you bring in those concepts to that? Yeah.
Does each substance have a different amount of like centrifugal force? That's why they separate.
Mm-hmm. Yeah. So it's, see, your force is mass times acceleration, and your mass is dependent on the density of the material, right? Right. Yeah. So once again, it's the absence of the centripetal force, because the viscosity and or the friction between the fluid and or whatever materials are there, it could be solids as well, and the tube, the walls of the tube, the inner walls of the tube. So that's not sufficient for you to bring it in. It's just the absence of that force making the fluid and or the solids to move out, right? So coming to polar coordinates, as I said, we always go from the knowledge that we know to the knowledge that we are trying to learn over here. The one that we know is your 2D Cartesian coordinate system, which is in terms of an x and a y coordinate, along which tangential to that, you have the unit vectors I hat and j hat, right? So when you have a particle of a certain mass m, which is not of any consequence in kinematics, neither are forces, we only are describing the motion here, right? So now we are able to mark the coordinates of this on this plane of the whiteboard as x and y. So as you very well know, this distance is now x and this distance is y, right? So now we are introducing an alternative to this. So alternative to xy for the same point, and we call that as r comma theta, right? Now that's the radial coordinate and that's the azimuthal coordinate. Okay. Now already you see a level of complication. Here you had x and y of the same dimension, which is could be length, which you could measure in terms of, let's say, meters or feet or inches or whatever you want, but essentially quantities of similar kind. Now you have quantities of different kind. One is still a length because your r is going to be defined as this outward distance here from the center, she call as O at 0, 0, and you have this distance r, which is what is getting into the first of these two coordinates, right? The second thing that you're having is what angle it makes with a positive x-axis in an anti-clockwise direction. Okay, so these are important things. It's very silly, it might sound, because these are things that you're already familiar with, but precision is very important in your description. Okay, so whether you're doing a homework or you're doing an exam or whether you're at work in your career, precision always helps, because it sometimes might be stating the obvious, but many a times it can avoid confusions. Okay, so stating units, for example, stating the frame of reference, stating the coordinate system and the direction of the sign conventions, which is positive in this case, anti-clockwise from the positive x-axis. Okay, so that's why I'm stressing that, and so that's your theta, because if you change any of that, it's okay, it's fine, but you have to be consistent in your entire derivation with that. So if you just need to stick to that, or whenever you change within your derivation, change the signs or whatever, okay, to maybe suit the rest of your derivation, maybe simpler with a different sign convention, that's fine, but just make that consistency in your entire approach, right? So this is your second coordinate over here, which is your azimuthal coordinate. Now things are very, very clear here. So now you have this as r. This is a right angle triangle, so you see this is 90 degrees. So this is the adjacent side and this is the opposite side. So you see that the opposite side is y. So you have your x is equal to r cos theta and your y is equal to r times sine theta, because cos theta is the adjacent side by the hypotenuse and your sine theta is the opposite side by the hypotenuse for that particular angle that we are interested in, right? So there is a easy way that you transform this from an r theta system to an xy system, right? So same thing you want to do the other way around. So when you want to do that, very simple, you just square these two and add them up. So if I square these two and add them up, I have on the right hand side, I can take the square in and it becomes r squared cosine theta squared and r squared sine theta squared. And if I want to add these two guys up, I get x squared plus y squared equal to r squared into c squared plus s squared, the thetas, and that goes to unity, as you know, for trigonometric identity. And therefore now I have a way of going from x and y to the r theta system. Just one of them is done so far. The other thing that I do is, without the need to square it, I just divide one by the other, the second equation by the first equation. So 2 divided by 1, and then I get sine by cos on the right hand side, which is your tan theta, is equal to y by x. Right? So what we are interested in is knowing y and x. I want to get theta, so it's very clearly your theta is equal to tan inverse of y by x. Right? So these two together constitute the inverse transformation from the xy system or the Cartesian system to your polar coordinate system. So these are things you would have derived as part of your high school math, just a revision of that, but there are certain subtleties or nuances that you need to notice over here. One, for example, this theta equal to tan inverse of y of x, is it a unique function or not? No, right? Yeah. So how many values does it have typically?
Well, I guess infinity.
Infinity, right? So because your theta can go over a circle 0 to 2 pi and keep on going. But now suppose I restrict my theta to be only between 0 to 2 pi, or equivalently I can say theta is between minus pi to plus pi, right? Now, is the problem solved? You said it has multiple issues. So as long as I have restricted it to just one rotation, because beyond that it's the same, right? As far as theta is concerned. If r is same, the theta is same, then theta is theta plus 2n pi, multiples, integral multiples of pi, 2 pi, then you are reaching the same point, right? Have I taken care of it?
No,
No. Why?
because first and third quadrant have the same inverse tangent, same with second and fourth quadrant.
Excellent, excellent. So what otherwise saying is that, so this is your first quadrant, second quadrant, the third quadrant and the fourth quadrant. You typically have all of the trigonometric identities positive in this. Only sine and its inverse of course is positive. Cos is positive, sorry, is TC. Tan here and cos here, right? So if all are, then tan also this is included in this, S, T and C. So you see that T is positive, as he says, in the first and the third quadrants, okay? So it could have the same values, in fact does have the same values, which is repeated at a particular angle theta here and a certain angle over here, right? So in other words, it's a dual valued function even after restricting theta to just one rotation of either minus pi to pi or 0 to 2 pi. So you have an issue there. So it's a dual valued function. So you need to take care of that. I probably mentioned this here. So many of you may not have used it, but at least you might have heard it. One of the software languages which was used extensively for engineering purposes in the past was Fortran, okay, standing for formula translation. And in 1961, within Fortran, there was a function which was introduced, which was called, instead of just arctan2, okay? And that had a way of restricting it to a particular single value, depending upon first testing whether x is positive or negative. And therefore, based on x, see, you can have, what is important here is the ratio y by x, right? So now y by x can be positive if y and x are both positive, or if y and x are both negative, right? In both cases it can be positive, and similarly your y by x can be negative if x is positive and y is negative, or y is positive and x is negative, right? So you just need to distinguish that. So you can do that instead of talking about both those things just in terms of the quantities, let's say x in both the cases, and then based on that you restrict your arctan 2 and arctan 2 kind of a function. So that is how you typically do that. And though it was started off by Fortran, this is kind of a standard in almost all the mathematical software, engineering software, etc., that some equivalent of this may not have the same name. It could be arctan 2 or whatever, but essentially it is there. So that's what kind of covers this. So any doubts on this? Yeah. So now we know how to transform from polar to Cartesian and from Cartesian to polar and take care of any non-uniqueness that might arise in the process. Now that's not enough in vectors or dynamics. You need the directions as well, right? So it's not just the coordinate, but also certain directions are important, which means unit vectors. So you need to transform the unit vectors as well, which is what we will try to do next. Or before that, so this is your arctan 2 if it's plotted versus y by x, right? So you, as was rightly pointed out by Atharva, you had at any given value of y by x, whether it's positive or negative, you see that you will have in general two values. Okay, so which of those values to be chosen depends on whether x is positive or x is negative. Again, depends on whether x is negative or x is positive, right? So based on that, you make the choice of what is that specific angle, right? So because the angle is read by the y-axis, so your once your y by x is fixed, it fixes a point on the or a line on the x-axis perpendicular to the x-axis, and then you have to choose between these two depending upon whether it is x is negative or positive. So it's a fairly straightforward, simple logic that is used to go from arctan to arctan 2. So yes, now even before we get to the unit vectors, we just want to, so in the previous slide, what you had on top you see is 2D, right? And so we called it polar. Now we want to extend it to 3D, very straightforward, simple. Call it, instead of polar, we call it cylindrical. The only thing that we have to introduce in addition is a z coordinate. So earlier in Cartesian we had only x and y, now we have a z as well. And similarly in the polar we had only r and theta, now we have a z as well, right? Now there's an alternative, the spherical coordinate system, which is very conducive for a lot of space dynamics, as I said, because most of your planetary bodies may not be exactly spherical. For example, the Earth is bulged at the equator. So in other words, the equatorial diameter is larger than your polar diameter. So you have more smashed up oval kind of a shape. But nonetheless, they are nearly, in terms of orders of magnitude, if you look at the difference is not that large. So typically you have spherical planetary bodies and spherical things like, for example, the path is elliptic, but if there is a perturbation to the gravity, it can become an ellipsoidal kind of a path, okay? Or if more than one body's gravitational force acts on it, you could have a slight change in the path. And these kinds of things are actually utilized in kind of changing the orbits of satellites. So orbital maneuvers that are done to go from one orbit to another orbit, many of these are actually utilized, and there many a times the spherical coordinate system becomes very useful. So you have the polar angle as well as the azimuthal angle, right? Now let's keep spherical for another slide. Before that, let's extend from 2D to 3D, that's from polar to cylindrical, by just the introduction of this the additional third transformation equation, irrespective of whether you're going from your polar to Cartesian or you're going from your Cartesian to polar. The only thing that you need is z equal to z, which is kind of trivial, that you have the same coordinate which is along the direction which is perpendicular to the plane, and we use of course the right-handed thumb rule to go from x to y, which direction of z is positive, that takes care of that. And similarly here in the polar coordinate system, from the positive direction of theta that we have, from that we take the direction of z to be that, because your ER is going to be always radially outward and your E theta is going to be in the increasing direction of theta. So your ER cross E theta in the right-handed thumb rule is once again going to be out of the board, just like EX cross EY was coming out of the board. Your ER hat and E theta hat, if you cross them, you get the EZ hat, or what we call as K hat is coming out of the board. So the only confusion there is in terms of the sign, because it's always perpendicular to the plane, whether it goes out of the plane or into the plane. That is taken care of by your dextral triad system, right-handed rule. So I think this is fairly clear and straightforward. There's nothing else that I need to say in this, right? Next, spherical coordinate system. One thing to be very, very aware of, something which is missed out even in many textbooks, is that there is a distinction in which, in the way in which mathematicians and physicists approach the spherical coordinate, and that's an interchange of the symbols that are used for the azimuth and yeah, so the azimuth and the polar angle. So you have to be very careful about that. Just make a note, and the same symbols are used, your thetas and phis, just that the meaning changes. You see, in the case of the mathematical notation, you have the polar angle denoted by phi and the azimuthal angle by theta, and in the other case it's physicists, and this is a kind of a standardized ISO notation convention which is followed in almost all of the physics literature. But every now and then you would see, based on their own backgrounds, authors might kind of get into these two interchange. Just be aware of that so that you're careful with the consistency. Neither of it is obviously wrong, just that you have to be consistent throughout your derivation once you choose a particular kind of notation, right?
Which one are we using?
Good question. Very interestingly, the so-called textbook for this course at Georgia Tech, the McGill and King, it just introduces the spherical coordinates only in a question, in a problem set. Not, it doesn't even have it throughout. So, and even there, if my quick browsing is probably right, they got confused between the figure and the expressions or the equations they had. Okay, so there was no consistency between that. In one of them, what was theta and phi became phi and theta in the equations. Okay, I might be wrong, but I just glanced through it this morning. So, so that's something that I observed. But that's something you have to be careful. So to answer your question, we'll not be using spherical coordinates in this course. Don't worry. Okay. So it may not be of significance. But the reason why I'm talking about it is that, as I said, in space dynamics, this becomes very, very critical. Even on the Earth, from the Earth's surface, when you're trying to measure, you have the latitude and longitude, right? So those angles are essentially, of course, it's in the other way around, because equatorial direction, we take the latitude as 0, right? So then we go on to 90 degrees at the pole, plus 90 degrees or minus 90 degrees or 90 degree north or 90 degrees south that you talk about. But the way it is used both by physicists and mathematics is measured from the polar direction 0, coming to the equatorial direction becomes 90 degrees. So that again, that subtle difference you should be aware of when you're using the spherical coordinates, right? I think I covered it. Again, another important point is sometimes instead of r, you use rho for the radial coordinate, and sometimes there might be an interchange between what is r and rho, because r typically is the distance from the origin of that point in which we are interested in. But here we are also talking of projections onto the xy plane, the projections onto the r theta or r phi plane, which is the azimuthal plane. So when we do that, this distance obviously is not the same as this distance, and sometimes this is called r and this is rho, or once again they could interchange that. So just be aware of that as well. Yeah.
And to get that, you just use the cosine, right?
Exactly. Cosine of this angle, okay, the polar angle, right? So cosine will give you this and sine will give you this, right? So if your r, you're multiplying by your sine theta, you will get this distance, which you could call as rho, right?
Oh, wait, so it's sine of that angle.
Yeah, because this is going to be cos, r cos,
Yeah.
this is going to be r sine, and then again you break this up into, so this is r sine of, in this notation, r sine theta. So r sine theta into cos phi would give you the x. R sine theta into cos phi would give you the y, right? And z, of course, is r cos theta. Right? So just be aware of this, especially when you're reading books or papers and things like that, not to get confused between theta and phi on the one hand and r and rho on the other hand, which is the actual radial direction and the projections. Okay, next, much time we have? Yeah. So polar coordinates, we look at vector transformation. So what we were looking at were just the coordinate transformations here, going from xy to r theta, and from r theta to xy, and we know how to extend it to z if it's cylindrical, and or to phi if it is spherical, right? Now, so whatever I mentioned orally over there is going from, of course, the r theta phi to the xyz. So similar thing like what we did over here can be done to get to the other way from xyz to r theta phi, right? So it's not, so most probably we will not revisit spherical coordinate systems in this course hereafter, but if there are any questions, I'll be happy to answer, not only now, but any time in the course, right? So coming to Cartesian coordinate system, the unit vectors we had in the planar, because we're talking of polar, not cylindrical now, so were just I and j, and the polar coordinate system unit vectors were er hat and e theta hat, and it's quite straightforward to get one in terms of the other just by using the unit circle. Now these are unit vectors, so their length is 1 and the directions are radially outward and in the increasing direction of theta. So that's your e theta and er. And now you can also introduce your I hat and your j hat, which are also of magnitude 1. So in other words, if you draw a circle, it will touch the arrowheads of all these 4 vectors, all 4 unit vectors, right? So that will be your unit circle with centered at that particular material point that we are interested in, which you can denote either by xy or r theta, right? So now very easily you can see that because this is theta, this angle is also theta. So therefore your er hat you can see is cos theta times I plus sin theta times j, because just by a vectorial addition to probably expand that and write it a little larger over here. So you're talking about this. So you see that this can, you can project it like this, and you would see that the projection of I times cos theta is what is there, and similarly your projection of j times sin theta, when you add both of them, you would get your er hat. Okay, same thing with the e phi, just that you would have the I hat contribution to be negative and your j contribution to be positive over there. So that's essentially the final result that you see over here. That, very similar to your xy r theta transformation, but the way in which it is derived is slightly different, that you're talking about that unit circle and the vectors of all of same magnitudes over there, but different directions, and you're kind of relating, whereas here you're talking of vectors which were having not only different directions, but you were talking of scalar measure numbers over here, all of which were different from each other, and that's what you were trying to relate. So don't confuse between the two. These are two important things, and though the results might look somewhat similar, but essentially one is transforming the coordinates, the other is transforming the unit vectors, which are quite different from each other, right? So, of course, this is a planar. We will go to the 3D in the next slide. So, the unit vectors in the polar coordinate system are not same at all the points in the frame of reference. So, unlike, so if I take this point, you have seen ER and E theta are over here. Your I hat and J hat are like this, right? If I take some other arbitrary point over here, another x naught, y naught, let's say, once again your I and J will be the same, exact same. Even though there's a translation doesn't affect vectors. It's only the rotation which affects, because they are unit vectors. Magnitude remains the same. All that matters is now the direction. So I and J remain the same irrespective of the point. But now I have to draw my R over here, and your ER hat will be like this, and your E theta hat will be like this, which means that your ER hat and E theta hat are functions of theta, but they are not functions of R. So if I take another point on the same line over here, the same radial line, then you can see that ER hat and E theta hat are different from what I have drawn there only by a translation, and therefore the magnitude and direction remains the same, so it doesn't change. So in other words, it's a function of theta, and that's also directly visible from these expressions that we got, that I and J are constant everywhere, and ER and E theta therefore depend only on one other quantity, which is theta, and therefore ER hat and E theta hat are functions of theta. So that's something that you have to keep in mind. And so are not same at all points in the frame of reference. They depend on the angle theta, as seen in these expressions or in the geometry as well. So unit vectors depend on space, though not on time. So the dependence on time could be an indirect dependence, but essentially what is important is that it's just that the theta dictates of a particular point dictates what is going to be the direction of ER and E theta. That theta, same theta, could be observed at various points in time with same or different R's as well. It doesn't matter. All that matters is the theta changes ER and E theta, not time, okay, directly. So with time, of course, theta could change of a particular particle, and therefore you would have ER hat and E theta hat changing with time indirectly. So it's kind of an implicit relationship. Then the particle moves in space, as is what dynamics is all about. This particle can be moving in space in any different way. If you're looking at a planar motion, within this plane only R and theta are changing. If you get into the cylindrical, Z also could be changing, but the particle is moving in space, which means that because of the fact that ER and E theta are functions of theta, since theta can change in general as the point moves, of course it can also move, that it's moving only on a radial direction without changing theta, except for that singular case. In all other cases, theta changes. If theta changes, ER hat and E theta hat change as well. So that's what we say here, that the unit vectors change, which in turn implies that the vector corresponding to moving particles, say, let's say for example the position vector or a velocity vector or an acceleration vector, all of these represented by unit vectors changing with respect to time. Okay, so this is an important distinction to remember as to what happens with the unit vectors and what happens with the other vectors, which are going to be expressed in terms of unit vectors, but typically you're talking about these quantities from a dynamics point of view. For example, acceleration changing with respect to time based on how the forces change with respect to time, and the integration of that with respect to time will give you the velocity changes with respect to time, and a second integration after applying, of course, the initial conditions, initial velocity in particular, will give you the position vector, where you again have to have the integration constant solved for by the initial position. So based on all of them, you would be able to completely solve the particular problem. Yeah. So maybe I'll just go through one more slide. Oops. Yeah. So yeah, if you're considering the motion in 3D space, So then of course you already had this position vector. I probably didn't write it explicitly, that if you go from O to this particular point, in the Cartesian coordinate system, you needed for planar motion two terms, that is x along I hat and y along j hat. But now you need only one term, which is r times er hat. Okay, so that's a very, very important simplification in terms of the number of terms that you're dealing with right at the position vector level, that it is just r the one of the polar coordinates times your er hat. And but of course, as we already saw in a previous class, theta is kind of implicitly contained in it because your er hat is a function of theta. Okay, it's just that you don't have an additional term. There's nothing like that. Okay, so there's only one term as far as planar motion is concerned. But now if you go to 3D motion, you have to add the either in a cylindrical coordinate system like this or in a spherical coordinate system. But in a spherical coordinate system, once again, the r that will be there will be er hat, which is a 3D kind of unit vector, and therefore you will have a difference over there. So this particular term is there only for the cylindrical, not for the spherical. Spherical, you still have that. Okay, but your er hat will now become a function of both theta as well as phi. You don't have here you had it as a function only of theta. You'll be having a, in the spherical coordinate system, you will have r is r times er hat, which is a function of both your azimuth angle as well as your polar angle phi, right? So again, as I said, there's a distinction between how mathematicians and physicists deal with it. So these could be interchanged, just keep that in mind. So once you have that position vector, many times we will use the notation R for it, but sometimes following certain books you could probably use the symbol P for that as well, but it essentially means the same. The reason why it's usually preferred in a cylindrical or a polar coordinate system, because R is used multiply for various other things as well, so you do not want to confuse it too much, so you typically use P over there. Velocity and acceleration are obtained quite directly from the fact that velocity is defined as now your v is equal to dp by dt in a particular frame of reference. So that's very, very critical, and I want you to focus on that, especially all of your homeworks when you're working out. Always the first step in any problem is you state the problem, you immediately after that you introduce a frame of reference, then you introduce a coordinate system associated with that frame of reference, because these two, remember, are not the same, not identical. For any given frame of reference, you have various choices of the coordinate system. So you introduce whatever coordinate system you think is simple or straightforward for that. There's no straightforward logic to say one will work better than the other. It's usually through experience, solving lots of problems you get used to, and then you say just by looking at the problem, yes, this for this a particular kind of inertial frame, a particular kind of coordinate system will make the derivation much simpler compared to the other. So not that you cannot do it with something else, just that it might be a little more complex. You'll be touching your nose instead of directly like this, you'll be going all around to touch it. So that's the trade-off you make when you make your choices. So those choices become very, very critical in terms of how fast you can solve the problem. In other words, how efficient you can be at your work. So we will go into these derivations based on that particular expression, because you remember as far as this term is concerned, it's quite straightforward because k is not a function of time. So all that I will have is z dot in velocity and a z double dot in the acceleration, but here I have a product, and so I have to have this uv becomes udv plus vdu, so you'll have lead to two terms. The first term is very straightforward, that you have r dot times er, but the second term involves an er dot. Once again, it's not a whole lot complicated, but it's more complex than just saying r dot times er. Because er, we have already written an expression in terms of cosine, sines, and the ij don't change, so all that I have to take the derivative of cosines and sines minus sine and cos, and then I have to put that. So of course that will be a derivative with respect to theta, But what we need is a derivative with respect to time. So you will have a theta dot also coming into picture, because there's a chain rule. When you want to take derivative with respect to time, first take it with respect to theta and take the derivative of theta with respect to time, which is your theta dot. So you will have a theta dot term coming there. So similarly, you will go to acceleration as the next step, and then we will make certain simplifications, and that's where you will see all that fake, fictitious stuff and also the real stuff. And we can make a judgment not from a physical argument that we made at the beginning of today's class, but purely from a mathematical perspective. Okay, thank you. If there are any questions, I'd be happy to answer. All right, thank
Do
you.
you have a new homework for material?
Yeah, I will.